Hello. You can hear me? Yes.
Yeah, we can hear you.
Thank you.
Hello, Professor.
So, welcome to week number 6, lecture B. It's weekend again. I'm standing between you and your weekend again. But I think it is exciting. We are in the end of the week number 6. So today, first of all, I want to go through a mistake I made in the last lecture. So very embarrassing. But none of you corrected me. So let me show. Do you guys see my screen? Yes. Let me show the video panel. Let me show the chat box. Let me close this float. Hiding floating meeting controls. Yes. Okay. Let me do a little bit bigger. Do you see the negative resistor? Do you see what I made a mistake? So this is wrong. Oh, why this is not working? Really, my pen is not working. So this is wrong. The reason this is wrong is because of this one. Why my pen is not working is because of this one. That's because of this one. Then I try again. Oh yeah, now it's working. Do you see that I use a KCL at this point? So you have I in here. This is correct. So about this I, so this is this I. Okay, this is I said 2V minus 2V divided by R. Is this correct? No, it's wrong. It's 2V minus this V. Okay. So this should be. So then there isn't anything called it's a 2V minus V. So there's not half R. So it's just R. Okay. Sorry about that. So be careful. So the difference between this R, this 2V minus V. Okay. All right. So good. So we are going to study the Bode plot. But I prepared some very interesting slides for you today. But before that, let's open this quiz number B. Okay. And to this quiz B here. So quiz B here today, I want you to recap what we did on this Laplace transform. So I told you last time 1 minus is wrong, should be 1 plus. Okay, should be 1 plus. Then after that, before end of the class, we are going to do this one together. I'll do this one for you, okay? But we need to go through the Bode plot, the procedures. Before that, let me do one thing with you today regarding this alternative way to do. So I got a t in here. I have sine omega t. So then sine omega t here, I have only half. Okay, only have half of this one. Okay, only have half of this sine. But actually, if you have sine, then you have everything like this, right? So then here it's what is this one? This is 2 pi divided by omega. Okay, so here is pi divided by omega. okay? Pi divided by omega. So actually you can see if I draw, I shift the sign. If I shifted the sign with this one, I shift it. So then if I draw something like this, so this one, this blue one, is basically is a sinusoid shifted. So it's basically you should write, this is a sine omega, okay? T shifted pi omega, right? Okay, pi omega. But is this correct? Because this is starting from here, okay? Nothing else, because everything is 0 on the left. So here we should write ut minus pi omega, okay? Okay, pi omega. If you don't have this term, basically you also have something like this. Go to minus infinity, right? So we need this term. So together, this is this one. So I know that this is so sine omega t is omega s squared plus omega squared, okay? And e to the power of minus pi omega s, okay? So this is correct, okay? But remember that this red one, if I don't truncate, I just say sine t omega t u t, okay? Sine omega t ut is basically this red one, okay, from this 0 here. So you can see this one plus this one, okay? So then you have cancel out here, or 0, right? So what's left is this thing in this shade. So here you got plus. So still, this is true. This is omega divided by s plus omega square plus this one. So this is still like omega s omega square and 1 plus e minus pi the omega s. So that is this. Let's say this is a gt. Laplace transform of my g of t is like this. Okay. All right. So clear. So again, this is plus. So this is also very clear, right? It's also very clear. So don't get very confused. So I hope you get it. So just write correctly. It's a pi over pi divided by omega. Okay. So, but how to do this one? I'll do this one, and we're going to do it together. Okay. So body plot. Let me do another thing here. It's called a comment. So I can draw on it. Then I'll make it bigger. Actually, I should do 100. Maybe 25. Yeah, this is better. So the step 1 is that you have a transfer function. So you have a transfer function h of s. So you have a pole, you have a 0, so p1, z1, and you have k is gain, and s is just the integrator. One of s is the integrator, okay? One of s is integrator. S is a differentiator, okay? So how to draw the body plot of this guy, okay? How to draw that? So the first you should do is to make it a standard form. This is not standard form. Standard form is to write 1 plus s divided by omega. So s divided by omega plus 1. Like this is a standard form. So that's why you divide it by Z, you pull out the Z1, you pull out the P1. So this is divided by P1. So that is the standard form. Okay, that's the standard form. Okay, so after that, you replace S with J omega. So whenever you see this one, is a J omega. Okay, J omega. Then we try to find out the magnitude of the transfer function. So the J omega here, you have a J omega, the S replaced with J omega. Okay, everything is J omega is S, J omega here. So this is easy, right? It's easy. So then we're going to do log 10, okay? 20 log 10 is to do a dB, right? So it's a dB, okay? It's a dB. Of this, actually a log of this one is magnitude. We're talking about magnitude, okay? We should put the magnitude sign in here, magnitude. So because we are using log, so then the product is plus, division is minus, okay? So the first one is 20 log K is this term, okay? You have Z is this term, okay? You have, then you have this one, okay? This term for the 0. Then minus, remember, minus, okay? Minus, because it's divided by. So minus, you have log 10 P1, so this is the P1, and J omega here, and you have this pole, okay? I think this is P1, okay? P1. So typo, okay, typo. So we can make the multiplication division into of this algebraic subtraction minus summation, okay? So each individual term can be shown in a logarithmic plot. You have, so you can see we have components in here, So this is J omega here, okay, J omega here. Pose and 0 at the origin, okay, it's this one. Pole 0 not at the origin, then you have a pole and 0 in here, okay. And we also may have complex conjugate poles and zeros. We'll talk this one later. Let's focus on this 3 types, okay? So when we can do the 3 types, we'll be able to do the transfer function like this, okay? So let's do step by step, okay? Then you add them together, right? So the first one, you have constant. So this is a log, this is a omega in a log scale, okay, log scale. So you can see this is 10 times, 10 times, 10 times. This is 10 times. This is called decade. This is called decade. This is another decade. So from 0.1 to 100, there are 3 decades. Okay. Oh, no, it's here. So, okay. So this is 20 log 10 and of this K, okay, of this K. So that's easy for constant, it's a straight line, okay, straight line. For all omega, it's the same, okay. For individual 0 and the poles at the origin, it's like this, omega. So it has to go to 1, 1, okay. When omega is 1, then J omega is 1 when omega is 1. So this is when omega is 1, okay. So then this H is 1. What is a log of 10, 1? Is 0. So this is 0 dB. So this is 0 dB, okay? So that's why you have the 0 dB of 1. So this point, you know it. Another thing you should do is you check the decade. So this is a 1 decade, right? So then you should check 1 decade. Then you should have something called 20 dB here. 20 dB here, because this is going to give you, you have 10 times, and then log 1010, it will 20, it will give you 20. So that's why this is a 20 dB. So this slope is called 20 dB per decade, okay? So the slope is 20 dB per decade, okay? All right. So going through omega is 1. So that's for 0 at the origin. But if you have 0 at, if you have a 0 at, so this is a 0 at the origin, okay? So it's S is in the numerator. But what if you have S in the denominator? Like our case, you have S in the denominator. So the same idea is you have negative 20 dB. Okay, so you must pass through the 1, omega is 1. Okay, and also you will see, oh, this is 1 decade. So this is another point. So that will give you a minus 20 dB per decade. Okay, so this is a case. This is the case here for S in the numerator versus S in the denominator. Okay. So that is for pose at the origin, okay, or 0 at the origin. But what if I have something not in the origin, okay? So for example, this is a Zi, Pi, so there's an omega here, there's an omega here, okay? So there's something called break frequency or critical frequency. Actually, I prefer you use something called a corner frequency. So the reason is there's a corner in here, okay? Corner in here. So what you should do is you have values Zi here, Pi here. So here you have Zi. In this case, Zi is smaller than Pi. Okay. So in this case, okay, Zi is less than Pi. Okay. Zi is less than Pi. Okay. And so this is your Zi. You have a breakpoint. Before Zi, everything is 0 dB. Okay. After that is, after this breakpoint, you have a positive 20 dB per decade. So this is the slope, 20 dB per decade. Okay. So then if you have a pole, then you have a breakpoint at Pi, then you draw that. So that is your edge should be look like this. Okay, should be look like this. So this is only for this red one is only for this one. This is a red one. But for this blue one, actually is 1/1 plus j omega divided by Pi. So this whole thing is this one. So these two should add together, okay? Should add together, should add together. So when you add together, so then you will see that how to add. 0 plus 0 is still 0. So together, we will get this one. And this is still 0 plus this one until here, okay? Until here. But you go upwards, go downwards, they cancel out. So this will make, let me do a different color. Let me do this color. So maybe this is better. So you have this one, this one, this one. This is for this edge. Okay, add together. So the red one is for numerator. The blue one is for the denominator. The green one is the add together. Okay, it's the total edge. Okay, make sense? Okay. But be careful, this is different because Zi less than Pi. But what if Zi greater than Pi? It doesn't matter, you just do something here, then you add together. I think it's similar, okay? So that will give you, so let's run through an example here. So supposedly you have a transfer function giving like this one. Sometimes this is also called a low pass filter. Okay, low pass filter. So to do that, to draw this low pass filter, we'll see why we call it the low pass filter, because low frequency they pass, high frequency they cut off, okay, attenuated. So the first step to write it is in a standard form. Write 1 in here, so you multiply 100 both sides, so your omega is 50, okay? So 50 is your corner frequency, okay? And you have a K is the gain here, is 0.01. So after that, we're going to draw. So we'll see that because 0.01 is a minus 40 dB, okay, 40 dB. So therefore, I have a minus 40 dB. This red curve, 40 dB is in here is for K, okay? And for the pole, the critical frequency is P1. P1 is 50. So here is 50, okay? So then what is this one? This is 10, 20, 30, 40, 50. So here we give you what? 100, okay? 100. And here we give you 1,000, okay? 1,000. So then this is your corner frequency because there's a corner, okay? So then you go down, and because this is the one grid in here is a minus 20, right? Minus 20. So if I move 50 to 200, 300, 400, this is 500. So when I wait, I think they did something wrong. It should be here. 200, 300, 400, 500. So it's here. So you should draw like this. Cross point is here, okay? So the reason it is here because this is this distance from 50 to 500. This is a decade, okay? And this is minus 20 dB. So that's the slope, okay? That's the slope. Then we put this, sorry, actually should be this one, okay? Should be this one. So this one should be 1 over S divided by 50 plus 1. So it should be like this, okay? It should be like this. So this dashed line, add to the dashed green one, red one, and this one, this together. Then final, this black one is what we need. It's 0.01 divided by j omega to 50 and plus 1, okay? So why we call this is a low pass filter? Because when frequency is lower here, this is low frequency, then it will pass, okay? It will pass, okay? When frequency is very high in here, it will get attenuated, okay? Attenuated is much smaller than the initial one. You get it? So this is a simple low pass filter, okay? Again, this is a log. This is a log, 10 omega. And this is a 20 log, okay? The log. So this is the first example for like low pass filter, okay? And remember, if you have a different K, it's as if you are moving this black line here, the black line in here, up and down, okay? Up and down, okay? Up and down, shift up and down. So now let's take a look another body plot in here. So what I have here, I got a numerator, I have an S. So what I do here, what I should do here, we need to simplify this transfer function in a form of product form. So in our case here, it happens to be like this. So S plus 5, S plus 500, okay, 500. So because of that, so it's not in a standard form. And this is standard form. S divided by this, F divided by this. So you divide it by 5, divided by 500, you come over here. So then what's left? What's left? This is 500 divided by 25. Okay, 500 divided by 25. It's 100 divided by 5 is 20. Okay, it's 20. Okay, so then this is my K. This is my K. So I have 3 things. I have 4 things actually. So I have a K is 1, and then I have a pole at 0. This should be 1, right? So it should be 1. And I have a 2 poles at the P1 is 5. So breakpoint, this is 5. Another one breakpoint is 500. Okay, 500. Okay. So I draw this one individually. So on the dashed lines are all individuals. So individuals. So be careful here. We did 20 log 10, 20. You need to use calculator. It's about 26 dB, okay? So in here, we need to do 26 dB. So this is around 26 dB, okay? So this is 20 log 10, 20. Okay. So what is the one with 1 of S times S? There's S in here. S will pass to 1. So this is 10 to the power of 0 is 1. So this is 1. Okay, this is 1. So this is actually is 1 over S. Sorry, this is S divided by something. Okay, but it's just S divided by 1. Okay, so this one will give you all the way go up and go down to infinity, right? So, but you need to pass 0 dB and 1. This is 1. Okay, this is 10. Okay. All right. So that is the blue one. What is about the 2 poles? One is at 5. So 1, 2, 3, 4, 5. 5 is here. Okay, 5 is here. So I have a breakpoint. So everything will be 0 dB. But at this point, I need to check where is my 50. So 10, so this is 5, 20, 30, 40, 50. So this is my 50. So this is this from here to here, this is 1 decade. So I need a minus 20 dB because it's in the pole. So this is a minus 20 dB. So therefore, I draw this dashed line. So this is like S divided by 5 plus 1. Okay. Same thing is true. We have 500, 100, 200, 300, 400, 500. So 500. Okay. Okay. But how I draw the line, I know the slope will be, this is 500. Okay. So then I need to do 5,000. So this is 1,000, 2,000, 3,000, 4,000, 5,000. So I should be this one here. Oh, no, this one, this one. So then I draw this one and as a line, okay? Okay. So then I add this thing together, all the dashed line, dotted lines together to form this black line. This is the final one, black line, okay? So this black line will give you what? So you just from here to here, you check. So you check. This is because of the constant K. So add everything here. You basically, you shift this blue line up, okay, up. So what is distance in here is the same as here. So it is 26, move up 26 dB, okay? So basically you move up here is 26 dB, okay? 26 dB, the same, going up until to a point corresponding to the 5. So this is a constant, you're already here. So, but you are going to continue go up, but you have something go down add together, go up and go down, the same rate, then you will be constant. So I maintain here constant, okay? Until to the 500 here, because here I have one going up, two going down, okay? This is going down, this going down, this is also going down. So add together, I have one going down, minus 20 dB per decade. So this is positive 20 dB per decade. And this black one is negative 20 dB per decade. So by doing that, you will see going up, constant, going down. What's that? It is as if you have a band pass. So I only go up and then constant and go down. So basically low frequency is not passing, okay? It's attenuated. High frequency also got attenuated. Only in the middle range is not attenuated, okay? So that's called, it's like a band pass, okay? It's like a band pass. All right, so this is example 2, okay? Example 2. So then let's go to example 3, okay? Example 3. They say, oh, this one is harder. Why? I don't think it's harder. So we first, I think this is want us to do it, or they have a worked out. Yeah, they have a worked out example in here, okay? First of all, example 3 solutions. Find the body log magnitude. So you basically need to make this a standard form, okay? So this is not standard form, but this is, okay? So you divide it by 20, both sides, so you got S divided by 20, so you have 20 in here. You pull out the 20, right? Then you pull out, so this is interesting, okay? It's already 1 in here, but they didn't write in this way. So S divided by 0.5 is 2S, okay? Then you have S in here. And here you need S divided by 20. So this is the final standard form, okay? Standard form. So you will see that in this case, you have 100 is a gain, okay? You have a pole at the origin, okay? You have a 1, 0 at 20, 2 poles at 0.5 and 40, okay? So what we do, again, we do, remember, we do all this component-wise. So again, we do the dotted lines are components. So the red one dotted in here, so this is K equals 100, okay? All right. So then, what is my, we need to check about x-axis in here. So where is the 1? So this is 1, okay? So this is a 10. This is 100. This is 1,000. So for the 1, I know that this blue curve, so from 1 here, so you have a decade in here, this is 0.1. So you have decade in here, so this is 20 dB. So it's the slope is 20 dB. So this one is 1/s, okay, 1/s. Now, we need to check out 1, 0, which is green. What's the breakpoint? Is Z at 20. This is a 20. So this is 10, this is a 20, 20. So it's 0 dB, but then you have a positive 20 dB per decade. So I have a 20 dB line. This is my 20 dB line. This is my 200, okay? So this is 200. So then we draw this line, okay? So this is my 0 at S divided by 200 plus 1 divided by 1. Okay, divided by 1. Now make sure you understand this. 20, no, not 200, 20, 20, 20, 20. No, 20 here. So this is break point, 20. That's why I need to double check. So that is for this one. And then we have a 2 poles. One is a 0.5. So 0.2, 0.3, 0.4, 0.5. So I have this yellow one, this guy is my 1/s divided by 0.5 plus 1. Okay. All right. And then what's left is another pole at 40. So 10, 20, 30, 40. 40 is here. So this color is my 1/s divided by 20. Oh no, is it 20? 40, sorry. No, 40. This is 20, 30, 40. So it's this point. So this is divided by 40 plus 1. Okay. Okay, so all these dotted lines we need to add together so we can sweep from low to high to see what's going on. So at this point, you can see you have here is a 20, this is 60, okay, 40, okay, you have 20, sorry, you have a 40, you have 20, you have 0. All three add together will be 40 plus 20 is 60. So this black line is the total. Then you keep going, then you're going, initially you're going like an integrator. So it's minus 20 dB per decade, okay? Minus 20 dB per decade. So then at this point, okay, you have one more minus 20 dB per decade. So this part will have 40 dB per decade minus, okay, minus. Then you get to this point, okay? So you are going to have this small section of minus 20 dB per decade because you have positive 20 dB, positive 20 dB. So you remove 20 dB from the minus 40 dB per decade. So this slope to here until here, okay, until here. So this is minus 20 dB. So after the 40, this is the 40, okay. After the 40, you got another one joining in here. So then you have a minus 40 dB per decade again, okay, again. So this black one is the overall body magnitude body plot for this transfer function, okay? So if we do step by step by this way, you can do all types of body plots sketched in this way. Okay. So this is a summary of all the techniques to get started. So I think we already went through these steps. Okay. But how about phase? How about a phase? Okay. Phase is the angle. Okay, it's the angle. So you have, we started with something called a K S plus Z1 and S plus, so we have S divided by S plus P1. So that's our original H of S. So then we write the standard form like this, okay, and put S is J omega, okay, that's J omega. So we want to check how we can compute the angles. You know that angles just simply you get every term's angle. Then you add all the angles together and minus the angles on the denominator. So the total angles is like this, okay? For all the constants, constants on the face, so there's no effect, it's 0, okay? But if you have a gain case is less than 0, it's negative, then you should not consider 0. We should consider plus or minus 180, okay? So we usually don't have that negative sign, okay? All right, so, but if you have zeros at the origin, or zeros, so at the origin, or then that means you have a j omega. We know that this j omega is actually can be written as, okay, the omega e j. Do you see that? Because this is a cosine 2 pi plus j sine 2 pi is j, okay? So that's why you have a half pi positive, so this is a positive 90 degrees, okay? Because the angle, magnitude is omega, the phase is here, okay? Similarly, if you do, so this is for s divided by 1, okay? What if you have s 1 divided by s? Okay, then it's opposite. So it's a negative 90 degrees. So, but what if this is something interesting? So there's a rule of thumb how you can do that. So if the zero not at the origin of the phase angle, say for example you have a zero term like this in the standard form. So when omega is very small, omega is 0, so it's a constant. So the phase initially is 0 degree, okay? 0 degree, okay? But what is the angle of this one when omega is infinity? So basically 1 plus j infinity. What is the angle of this one? Is okay, okay. So when omega is very big, so omega is very big, so then it will be 90. But what if omega is z1? When omega is z1, then you will have 1 plus j. When omega is z1, you have 1 plus j. Well, 1 plus j is nothing but what? The square root of 2. Okay. No, it's actually no. The magnitude of this one is a square root of 2, j 4 pi, 45 degrees. Okay. 45 degrees. Why? Because you have a cosine 45 plus j sine 45 times square root of 2 will give you what? 1 plus j, okay? Because cosine 45 is half square root of 2, okay? I need to turn my mail off. Okay, so basically when omega is 1z, is z itself, this is z, then basically my angle is 45 degrees, okay? So this is my 45, okay? So the rule of thumb is to do 1 decade left will be 0. 1 decade up is 90. So then you draw a line between here. So that's the asymptotes of your phase angle transition. It's asymptotes. But in reality, it look like this. There's some slight transition here. It is very close, very accurate, okay? But you need to pass this point for sure, right? Because it's a 1 plus j. This is a 1 plus j at this point. When your omega equals z1, okay? So it's different. You need to shift left for 1 decade, 0.1 z1 and 10 times z1. So because this is true that we can say that 0.1 z1 is less than z1. And we can see z 10 z1 is greater than z1, okay? So when 1 plus j omega z1. So you can write very small. Z1 is very small. Okay, so that will be 1 plus j01. So this is a 1 plus j times 10. So this is approximated like 1. This is approximated like 10j. Okay, so that's why you have this asymptotically 0. This phase angle is 0. This phase angle is 90 degrees. So why you have this one? Okay. So it's going to be 2 decades. 1 decade up, 1 decade down, around this Z1. Okay. This is the rule. Okay. Because we need this reasoning. Okay. We need also this type of reason. Okay. Wait. Sorry. This type of reasoning. Okay, this type of reasoning. So that's for 0. What about my pole? My pole is like this, standard form again, a standard form. So we can see that how to draw its phase plot is the same. So you have P in here corresponding to 1 over 1 plus J, okay? Okay, so then this is 45 minus, okay? So this is 0, okay? And this is minus 90, okay? And you have a 1 decade up, a 1 decade down, okay? 0.1p. So then you draw a line between these two, okay? So this full thing is called a phase magnitude. The phase body plot. Phase body plot of basically this is a low pass filter, okay? So I think now we can check the body phase diagram for the previous examples, okay? Really, sensitivity. Yeah, thank you. So let's check, let's go back to this guy, okay? Let's go back to this guy, and we write in the standard form. The magnitude 1, we already know how to do it, okay? So the magnitude 1 is this one. You have corner frequency 50. So then below all the 50 will be, this is a 20 log 10, 100 will give me 40 dB. Okay, so I have, oh no, the minus is 1 over 100, so it's minus 40 dB. So it's minus 40 dB. This one, then I have a decay, so this slope will be minus 20 dB per decade, okay, per decade. But what about my, so this is my corner frequency. So I put 1 decade in here, divided by 10 is 5. Times 10 will be 500, okay? So basically at 5, I'm 0 degree. At 500 is minus 90 degree. Then at the 50 here, corresponding here, should be minus 45 degree. So I just pull out 1, 2, 3, then I can draw this transition line. So this is my phase. This is my magnitude, okay? Magnitude. So the whole thing, magnitude and phase, whole thing is called body plot. So the body plot should have 2 parts. One is a magnitude body, one is phase body plot. So this is log 10 omega, this is log 10 omega. Get it? All right, it's clear? So let's repeat that here. This is very interesting. We are going to draw it. So we have done this we have done this this part already, right? This one in the standard form. We want to check. So I say this is a band pass filter, right? Band pass filter. You only pass during this band pass. The others just attenuation, right? Attenuation. Okay. You get die out. So you did this signal processing already. Okay. So we are going to check how we can do the phase. Okay. So the phase basically is also you have a log 10 omega here. Okay. So this is a 0 degree, and we check everything one by one. So again, for the blue one, for this blue line is the blue line. What is the blue line? Blue line is this guy, this S. Okay. So this one is the angle for S divided by 1. Okay. Okay. And this one is the magnitude of S. Sorry, S divided by 1. Yeah. Okay. So that's the phase, 90 degrees, positive, constant. Okay. But if you have a orange line, this is a constant, so that is positive, so it's 0. Okay, it's 0. We don't care about it. Okay, so what is this one? What is this orange one here? So basically, it's something like this. Okay, so it's S divided by. So this is the center frequency. Let's go back. Let's check the center frequency. 5 and 500. So I have 5 in here, 5 in here. So I have 500 in here, 500 in here. So when we do the phase, we need to identify where is my 5. My 5 is here. Okay. No, my 5 is here. Okay. My 5 is here. This is my 5. So I know that we need to pass minus 45 degrees. So this is 45 degrees. Then we do this one, this is 0.5. Okay. We break the 0.5 to 50. So this is 50. So then 50 hertz. This is a minus. This is a minus 90 degree. So this orange one follow the same rule we just used. Okay, we just used. On the other hand, we are talking about this one is 50. Okay, this is 50. So we are going to check. So we have a center line here. This is 50. Okay, it's 50. So they will corresponding to minus 45 degree. Okay, so then we need to do a 5. Okay, this is 500, right? Let me go back. Yeah, it's 500. I'm wrong. So this is 500. So sorry. In here, this is 500 of this point. So then corresponding to minus 45 degree. Okay. So divided by 10, you have 50 in here. So you have 5,000 here. Okay. So this is minus 90. So this actually cannot see clearly, but let me draw this one. So this guy, then turn this one and turn this one. So that is your 1 over S divided by 500 plus 1. Okay. Okay. Now you add them together. You add them together. So everything is 0 here. This is 90. So I keep 90 here. Okay. Until I see going down, I also go down. Go down and to the point here. Then this is constant. Then this is still going down. until to a point, will become a constant. Yeah. Okay, become a constant here. So that is interesting part. The whole thing is from positive 90 degree to minus 90 degree. So that transition. I hope this is also clear to everybody. Okay, so phase plot, Bode plot. So then we can run another example here, and I guess you can run through this yourself. Can you? So this is the magnitude. Then this is the phase. Okay, this is the phase. So I would like to suggest we walk through one of this one here, because you need to do this one yourself. You need to go through that thought process, okay? You cannot simply say, oh, sit here, listen, without reading books, without doing homeworks, without going through the thought process. Then you are not learning, okay? So what I should do here is to consider this is a standard form. What is the standard form? I learned something here. So standard form is S plus 1 here, S divided by 10 plus 1. Okay, so then you need to do what? Here you have 1 over 10, okay, 1 over 10, right? 1 over 10. So you can see that we have two breakpoints. One is at 1. So this is a 1, okay? Another breakpoint is 10. This is another breakpoint. So if I do S plus 1, what is S plus 1? S plus 1 will be S plus 1. Okay, so this is my 1. Then I need to go up. So how can I go up? So I'm going to check 1 decade is here. So this is 1 decade. I need to go up for 20 dB positive. So then I connect this line, and this is going to up. So this is for S plus 1. So then I'm going to do another one. Is let me do the purple. So another one is 1 over 10. 1 over 10, 20 log 10, 1 over 10 is what? Minus 20 dB, right? So minus 20. So this thing is 1 over 10, right? But what is S 1 over, what is 1 over S plus 10 plus 1? What is that? I'm using a different color. So I'm using the green color, okay? Green color, I know that I'll be always 0 dB until to a breakpoint. Because it's a pole, I need to go down at the rate of minus 20 dB. So what I do is I check what is my 1 decade. My 1 decade is here. So then where's my minus 20 dB is here. So I'm to connect these two lines, and it will continue. Okay, will continue. So using the tradition here, I'm going to use a very big dot. So then I scan the from low to high. So then everything will be minus 20 dB, okay? Until to this point, because I add this thing together, so then I know I'm going to have this black line in here, okay? Until to this point, okay? But after this point, I'm going to have going up and going down, they cancel out. So I'll keep this. So this black, the black line is my magnitude body plot for the original body plot, okay? Magnitude body plot. Do you get it? So I'm walking you very slowly. I expect you will be able to do this and follow this, okay? Now, let's do another one for the phase magnitude. So let me do the same idea here. So I do so for this pole, for this S plus 1, what is a breakpoint? 1. Okay, so 1. But remember, at the breakpoint 1, it should be minus. It should be sorry. It should be positive. Should be positive 45 because it's in the numerator, right? So this one it has to pass. Then I go 1 decade less, which is here. Okay, 1 decade less. This will go to 0. Okay, everything beyond that is 0. Then you have a decade up. So then you have 90 degrees here. So your face will be look like this. Then you will be constant at 90 degrees. Okay, 90 degrees. So that's for the S plus 1. So what is for S? What is the for this term? Okay, again you check where is your breakpoint. It's in the numerator. It's in the denominator. So you're at the point that you will have 1 plus 1 plus j in the breakpoint. S equal j omega. J omega when omega is 10 is 1 plus j. So this is a minus 45 degrees is here. So this is a 10. So this is a minus 45. Okay, it will be always 0 until you to 1 decade less is here until this point. Okay, is 0. Then you cross this one to another decade up, you have a minus 90 degrees. Okay, so then you connect these 3. Okay, this 3, you will get this one. So you will get this. Okay, okay. So should we consider 1 over 10? No, we don't need to care about it because it's a constant. It's a positive constant. So it is 0. It phases 0. I don't need to draw those gains at all. So I can directly come out with. So what I'm going to do is the whole phase should look like this. So you have phase is 0. Until here, your phase will go up. Okay. But you can see you go up and you go down, so you will be constant until to this point. Then you start to get down like this. So, okay. So, but remember, what I did was wrong actually. I need to correct myself. Okay. So here, when you get to the minus 90, it should be constant. Okay, it should be constant. So it's not like you keep going down. It's not like a phase. So you should go something here. Then you keep a constant at the minus 90. Okay. Keep constant. So therefore we have the same thing here. We need to draw this one. Okay, to here, and then you can see we should keep this one constant. Okay, because this is a constant, this is a constant. Okay. All right. So this is, you can see here and here. So this is 0 degree. This is also 0 degree, right? So 0 degree, then you have a area is face leading. Then after that, you become, it's kind of like a bump, okay? When you drive on the road, you have a bump, right? It's like a bump. So go and constant, go down and 0. So, all right. So isn't this interesting? So this is 45. Okay. But in reality, if you do a real thing, you will see your face will be look like this. It's quite close to, okay? Quite close to. Do you know how to do this now? Okay, so you can see overall the phase across the omega, the phase is positive. Can you see that, this phase angle? So overall, we can see this is a leading filter. I'm adding some phase leading, okay, phase leading. Of course, I lead differently at different frequencies, okay? Okay, so low frequencies I lead 0, high frequency also lead 0, but in some of the frequencies I lead bigger within the range. So this is also called lead yeah, it's called lead lag filter. Okay, so because the system is going to lead first, then come a lag, then become 0. So it's lead and lag. Okay, so the pole is smaller. The 0 is smaller than pole, but it could be opposite. Okay, so if you have a s plus 10 divided by s plus 1, so what's going to happen? Okay, so this actually is called lag lead filter. Lag lead filter. Lead lag filter. So you lead first, you lag. You lag first, you lead. So you can imagine the phase would be something like this. I need a fancy color. Let me do this. So then if we do this one, then you will see that the phase will be something like this. It's just like a flip it, okay? But you can imagine that if you have a, then you will have something like this. So you have 10 in here because 10 is in here, so you got something here. So instead of starting from minus 20, you start with positive 20, okay? Positive 20. When S is 0 is 10. When low, very low frequency, so S is 0, S0 is a 20 dB. So everything is 20 dB until you see the 1, okay? 1 will be, you will have something like this, okay? Yeah, you go down, okay? Then you go this one again. So it's something like this. So this is overlapping here, it's overlapping. Because in a high frequency, so you become 1 plus 10 divided by S, 1 plus 1 divided by S. Okay, when S is very big J omega, so then you can cancel out this term, right? It's almost 0. So 1 divided by 1 is 0, is 1. Okay, then 20 log 10, 1 is 0 dB. So this is 0 dB, right? So in the high frequency, they are the same, okay? So this fancy color is we just draw is a lag lead filter, okay? A lag lead filter, okay? You do the lag first, and then you lead. So you go to the pole first, then you have 0 numerator panel. So lag lead lag. So if I give you things like this, no. If I give you things like this, I say, tell me, is this a lead lag or lag lead? Can you tell me? I hope this picture will give you a good impression. You will be able to do this one for me, okay? And do it, okay? Maybe it's a good idea. You make a screenshot, so then digest a little bit. When you draw and you feel stuck, you look back, okay? You look back. Good? Okay. So I'm done with my body plot. Only thing we didn't do is the second order one. We haven't done the second order one. We have the second order one. We need a separate. I think the phase, we know the phase. It's okay. So I think we can say we finished that except the second order one, okay? The second order one is a little bit involved. We need to spend more time on that. It turns out we used up our lecture time. So I have something, so wake up, I have something funny for you, okay? I hope it will motivate you to study your work. Have you ever seen a humorous cartoon like this? Okay. So that you need Fourier analysis actually. So you need to show all these equations to do the analysis. So I'll upload this slides. I just made the slides. So I think you probably already know that for any of the signal, okay, any of the signal, you will be able to write your function into this called Fourier series expansion. And those coefficients can be obtained this way, A and B and A0, B0. So basically, it is something you have learned before, but now you are using a basis function like this one to represent the signal here. But if you feel this is uncomfortable or strange, let me remind you something you have learned already. Do you guys know that's Taylor series expansion? Okay. So then it's basically you are saying that you have 1, you have x, you have x squared, you have x cubed, da da da. So this is also a basis. Okay, it's you write in terms of this one, then it's a Taylor series expansion. If you write this is also a basis. Okay, so the sine cosine with different so this is also basis. No, not basic. Sorry, basis. So this is also a basis. Okay. Okay, this is called a polynomial basis. So this is called trigonometric harmonic harmonics basis. So you basically are using the basis linear combination to represent your signal, but using the property of orthogonality. So this is called orthogonal basis. But Taylor series, the polynomial basis is not orthogonal. Orthogonal, okay, orthogonal. So this is basically the property of orthogonal, okay, orthogonal. So then we get an example to show that, in fact, we are artificially making this signal in this interval. We care about it and make it periodic. So you can write down its coefficients, okay? And write down its phase, okay? In a complex format, okay? So this is called a compact notation. Using, because of this term, you can write always like this. So you always can combine this one with phase and amplitude. So you put amplitude in here, put the phase in here. Okay, so that gives you a Fourier series analysis. Okay, so this Fourier series analysis has some limitations. You have to be periodic. So therefore, later on, we prefer to use Fourier transform. Okay, so Fourier transform, Fourier. So then there's another thing called convolution. Okay, convolution is even more interesting. But unfortunately, I cannot show you. But I want to flash you one cartoon. We are going to go through this cartoon next time. So I'll just flash you. I'll stop my sharing. So I'll make up all those things missing in your knowledge structure. So I hope make your life easier. I'll do that next time. See you next week. Have a good weekend. Any other questions? Let me see. Yeah, have a good day. Yeah, good rest of the day. Bye-bye then.
Thank you, Professor.
All right, see you later. Bye-bye.